Dr. Amarjeet Kaur is a senior professor of physics at the University of Delhi, specializing in experimental condensed matter physics. With a distinguished career spanning decades, her recent research focuses on sustainable energy solutions, including the development of supercapacitor electrodes from mustard seed biowaste. Dr. Kaur is a highly respected academic and dedicated mentor to aspiring physicists across India. She also holds 7 international patents, reflecting her significant contributions to innovation in her field. So with that, I would like to welcome Dr. Amarjeet Kaur. Please let me know if you're able to share your screen. Are you able to hear me? So sorry, there were some technical difficulties on our end. Um, could you try to speak just so I can make sure I can hear you?
Yeah. Hi.
Okay, perfect.
Am I audible?
Yes, you are.
Okay, great. Should we start now?
Yes, please do.
Okay, let me share my presentation. It says that sharing is not turned on.
Oh, one
Send
moment.
request.
Okay, now you should be able to. Are you able to share now?
Sharing. I'm just opening my.
Great.
Yeah, and is my screen visible?
Yes, it is.
Okay, so I'm just doing the slideshow of this presentation. Hi. So good morning to the organizers who are in Canada, and good evening and good afternoon to the entire world, wherever people are listening to this talk. So today I'm thankful to the organizers for giving me the opportunity to talk and deliver my lecture at this forum. And I'm going to I'm going to talk about the sustainable supercapacitor electrodes from the mustard seeds biowaste, because it is an entrepreneurship session. I'm delivering this talk, and I am once again thankful to Dr. Conrad for giving this opportunity. So this is the overview of my lab. Like, we work in the area of organic electronics, basically in OLEDs, solar cells, and our recent venture is supercapacitors and batteries, and EMI shielding, charge transport, gas sensors. We are working in my lab. So this is my department. This is a small glimpse of my department, and this is the science block in our university, because I belong to University of Delhi, and we have 7 lakh students, and we have the undergraduate colleges distributed all over Delhi, and we have postgraduate departments. So this is the glimpse of the science department. Like, this is this mathematics department is there, anthropology is there, geology is there. So we have different kind of departments in the science block. Then we have this rugby stadium and all. So so I work in this department of physics and astrophysics in Delhi University. So coming to my talk, I don't know what is stuck here. Okay. So my talk is related to supercapacitors. So here I'm going to discuss the electrochemical performance of the porous carbon produced from the biowaste of yellow mustard seed. And we are interested in pursuing this research further because of the promising parameters which we have received, which we have got in this device. Now, the electrolytic double layer capacitor has gained a lot of interest because of its application, because of high charge storage and fast charge discharge. So, so this is a very important parameter for any device where you need a high charge storage. So here we are using electrolytic double layer capacitor. Basically, we have the electrolyte sandwiched between the electrodes, and these two electrodes can be symmetric or asymmetric. But the basic idea is that the charge should be trapped at the interface of the electrolyte and the electrode. And more the charge is stored, more is this capacitance value. And so the charge is stored basically because of the interaction of the electrode with the charges just stored here. This is basically an electrostatic interaction. And the charge transport takes place through the electrolyte medium because the charge is stored on both the plates. And that is why it is the electrolytic double layer capacitor, because here we get the double layer of the charges. And coming to just a basic physics, so we can have, the device just follow this uh, the simple physics law. And so basically, and we have these three different layers of the charge. This is the electrode, right? So in this case, we use the carbon electrode. There can be other electrodes also. So and then we have the ions. Like suppose if this charge is positive, this plate is positively charged, then the negative ions will be naturally get electrostatically attracted towards it. And then so so this is the main layer, but in between, the negative charges are trying to come here. So there is a Helmholtz layer in between, because there, this is electrostatic interaction is there, but the ions are still not trapped here. And then we have the another layer, which is the diffuse layer, because where the charge is just starting diffusing. So if we calculate the potential at all these different layers, okay, so total charge we get, like this is the basic Helmholtz formula. So that is the total capacitance derived from this is the Helmholtz capacitance plus the diffuse layer capacitance. So this is the entire capacitance of this capacitor. So the supercapacitor, the market is going tremendously. You can see the US market itself is getting doubled in next 2 years. So and because as I told you that the basic property for a good supercapacitor is a high charge storage, so that you have the high capacitance, and second is the quick charge discharge. Because of this, it is used in the electric vehicles as an ancillary battery, as it's a part of ancillary battery that that when the electric vehicle you have to just start it, so that you need a tremendous amount of charge to be dissipated immediately, to be given immediately. So that for there the supercapacitor helps. Then in the UPS system, energy harvesting, there are so many applications nowadays where the supercapacitors are being used. So any supercapacitor is characterized by the two things, that is the power density and the energy density. Power density is that how energy density is how quickly you have the charge which is dissipated, and the power density is measure of how quickly this energy can be. Rate of change of this electrostatic energy gives you the power density. So generally we have it's the case of symmetric supercapacitor, where both the cathode and anode, the positive or the negative electrodes are symmetric, right? So there the energy density is is low, right? And the energy density for the batteries is comparatively higher, and the power density for the capacitor is very high. So in the case of conventional supercapacitor, in the conventional capacitor, it is of the order of 10 to the power 5. So supercapacitor, the case of supercapacitor, the power density now is lying between 10 to the power 4 to 10 to the power 5 for the research grade devices. Now coming to why we have chosen mustard, because mustard is a very popular crop grown almost in every state in northern India, and the mustard oil which comes out from the mustard seed is used as a general household oil for cooking and purpose. So the seeds, once you are extracting the oil out of it, right? So there is a lot the skin which is left. It is used as the fodder for the animals, but still there is a lot of this thing before the mustard seeds get wasted. The skin gets wasted. So from the mustard seeds, when the oil is extracted, then we wash that skin and then we dried it at 800 degrees Celsius. So to get this bio waste, and then we crushed it, and again we washed it, we treated it with sulfuric acid and potassium hydroxide, and then we again activated it in furnace to get the activated carbon. So this carbon is different than the usual carbon powder, in the sense it is more porous, because we need pores on the surface of the electrode to trap the ion. So basically this is how it is happening. Then once we are using porous electrode, the charge gets trapped in these pores. So as a result, we have the the surface area available for the charge trapping increases, and hence the total amount of charge which is trapped at the electrodes get increased. So this is the main reason for using these kind of porous electrodes. So that is how we are making the porous carbon electrodes. Now coming to so this idea clicked us, as I told you, because we have a lot of waste, tons of waste of mustard skin is there, though it is fed to the fodder as a fodder to the animals, to the kettles. So this is the same images which shows the voids in this activated carbon. So basically, when we developed the electrode, so we developed it on the graphite sheet. So for making the device, we put the slurry of this activated carbon on the graphite sheets. So this is the graphite layer which you can see, on which this is the activated carbon, and you can see the voids in this activated carbon. So these are the measurements which we did collaboration with UK, because we wanted to see our collaborator in United Kingdom. So here the STM images are there, and you can see that and this is the contrast image, that here we can directly see these pores. These pores are taken in the contrast image, that is, instead of black you can see them as the white dots. So these are the pores which are of the order of 2 nanometers. So this is a very small pore, and it is apt for trapping the ion. So the EDEX study shows that the atomic fraction shows that we have the 90%, 90 to 95% carbon is there, and a small amount of oxygen is also there in our activated carbon. So this is the nitrogen absorption isotherms and the pore size distribution of our material which we have developed. So you can see that the it, you can see that there is a surface volume over here, and the surface area. So the surface volume is around 563, sorry, 0.3 centimeter cube per gram, and the surface area is around 563 meters square per gram. And so there are, you can see that XRD shows typical amorphous distribution. This is the 200 plane, and then we have a sharp peak at 32 degrees, where the d spacing lies around 0.79 or the 2.8 angstrom. So both the peaks themselves, they show that there is a highly disordered state. So we did the Raman spectroscopy of the same powder for the same sample, and then we have this D band and the G band. So we are getting both the peaks in the Raman spectroscopy. The D band is indicate the order of disorder in the material, whereas graphitic band is related to sp2 hybridization. So you can see that more than that, we have second order bands are also there, which are again the measure of disorder and which is expected because we are not making any crystalline plane out of it. It's just amorphous carbon. So, so now coming to the device. So we have the activated carbon deposited on the pipe sheet, and in between we take the PVDF H2SO4 slurry as the electrolyte. So the device comprises of for any device we need to characterize it, and the important parameters are like we have to measure energy density, power density, what is its capacitance, what is the cell weight, how kind of IV characteristics we are getting. So all these measurements are done using cyclic voltammetry and electrochemical spectroscopy and the galvanostatic charge discharge. So this is the our device configuration as shown here. So we have the electrode material, right, on which you have deposited the activated carbon, and then we have a filter paper, sodium sulfuric acid as the electrolyte. So you can see that initially we do the cyclic voltammetry. So for the initial voltage rate, we are getting almost a rectangular shape, which shows the typical, which is the characteristic of any capacitor showing the maximum charge storage. But gradually you can see that this is deviating away from the square shape because of the diffuse transport, diffuse ion transport. So this is the reason for getting these kinds of shapes. Then we did the galvanostatic charge discharge measurement, which are almost symmetric. You can see here, and they are being done um, at different rates in terms of the current. That is 0.25 amperes per gram, 0.5 amperes per gram, and so on. So the maximum value which we obtained from these, we did from this we calculated the specific capacitance, that is the capacitance per unit gram, and it turned out to be 198, which is the maximum which we have got. It's 198 farad per gram, and this is a very good capacitance of the industrial application of the capacitor. So we got this is the current this is the value which we have, the maximum capacitance value CS we have obtained for the current density of 0.5 ampere. So then this is the, so if you can look at the specific capacity versus current density, so this is on, this almost remains constant for the small current density value. So we try to modulate our, try to develop the model for our device, and it seems that it has some series resistance, right? And the parallel resistance with along with the Wagner resistance. So all these series resistance, which again these measurements we did by EIS spectroscopy, and the maximum value of series resistance we just got is 4.5 ohm, whereas the R3 and W is around 25 ohms. So it is a very good, that is for the device performance, it is very is preferable to have a very small series resistance, and having a 4 ohm resistance is pretty good because it will not hamper the device or it will not cause the device loading. Whereas um, the parallel resistance up to 25 ohm is then fine for us for making any device. So this is the equivalent circuit for the for this device, and you can see from this Z double prime Z prime four plots that initially there is a small, very small circle here. Yeah, it starts increasing, then we have a straight line curve. So here in this region it is purely capacitive, and then it becomes resistive. So up to 25 it is safe for us for having a capacitive behavior. So the power density again which we have seen, which calculated from this galvanostatic charge discharge, is we are getting very pretty good and very constant value of the power density, that is around 10 to the power 4 watt per kg. And even with the change in the energy density value, its value of the power density remains constant, and the charge retention and the capacitance retention also to 2000 cycles. It is fine. After that, we find that there is a decrease by 20%. So there is a 80% retentivity of the capacitance. So now, right now, we are working to improve its retentivity so that because although we have achieved commercial grade values for the specific capacitance as well as the power density, the retentivity is just a 2000 cycles on which we are working so that it should at least go up to 20,000 cycles and then again, and then maybe further we can improve it up to 50,000 or 1 lakh cycles for the commercial application of this device. So far from this device, if we compare it with the work of the other people, because the specific capacitance received by other important on the mustard seeds itself, because even they have used the mustard oil by they have just used the carbon soot from the mustard oil directly rather than making the rather than achieving the activated carbon from the skin of this mustard seeds. So in any case, if we compare it with these bio waste, so our value so far is better than the any other value reported in the literature. So hardly there are three or two or three reports there are there. So if we compare, so our results are more promising. But now we have to develop the commercial grade device out of it. So in the conclusion, we have synthesize the activated carbon material produced from the biowaste of the yellow mustard seeds. And using this carbon, the device has a mesoporous structure with the specific area of around 563 meters square per gram and has the very good electrochemical performance. And because it has the high specific charge, has high specific capacitance of 198 farad per gram and high power density of uh, 10,000 watts per kg, the cyclic stability of 2100 cycles. And the best thing is that we have obtained a very low value of series resistance, and the charge transfer resistance is also 29 ohms, which indicates its potential as the prominent electrode material for environment friendly and stable, sustainable electrochemical energy storage devices. So at the end, I would like to acknowledge my entire group, my research scholars and postdoctorates who are working with them. And this is the setup and facilities which we have used for this particular work, which includes our synthesis in this low temperature bath. And then we have the we have this electrochemical workstation, and we have vacuum techniques for depositing and everything. And so with this, I would like to thank you all for giving me, for listening to me, giving me the opportunity to talk here at this forum. So now you can ask me the questions.
Thank you so much for your presentation. That was very interesting. There's a question in the chat. So it says, wonderful talk by Professor Kaur today. I have a quick question. Why did you choose mustard seed biowaste for making supercapacitor electrodes? Also, does the material from mustard seed store energy efficiently? And how does its electrochemical performance compare with conventional carbon-based materials, say carbon nanotubes?
Yeah, well, actually, you need a porous, you need porous electrodes, right? So we have developed, we wanted to develop anything from the bio waste. Our other work is like we have used this pulp from the juice, from this juice industry, like the mosmi, you say, or the citrus fruits. We have used their pulp also because we wanted to use as a waste material, something which is, which is a waste material and which is produced in bulk, and then you have to throw it or it burn it. So basically, so that is why we have used the mustard seed. Like people have used the tree barks also, they have used flowers also, but our main focus is, like as I told you, that mustard is grown almost in all over northern part of India, and it is used for the edible oil. So the after extracting oil, there's a lot of lakhs of tons of this thing, this skin is left. Even it is fed to fodder, and after that it has to be burned also. So better is to make some device. So this is the basic idea of using the and this mustard seed carbon activated carbon. Yeah, but we can try other materials also. But our concern was that whatever waste is produced in bulk in our country, so let's try with it.
Yeah, that makes a lot of sense. Another question I have is after it becomes after its process of becoming from mustard seed waste to I forget the term you use specifically. Is
Supercapacitor
there
device, yeah.
yes. Is there any other waste with that, or is it just like you can use it and that there's like no waste after? If that
After
question is
using it, there's no waste. Once you have made the
I
activated
see.
carbon, then you the entirely see because for we are testing device in our lab. So in lab we need very the amount of material required is hardly few milligrams. Okay,
Mm,
but because the industrial scale capacitors are very good in size, so there you will be requiring this material in bulk.
I
So,
see.
because to make a large scale capacitor, so then the capacitance will also increase. So for example, if you are going to use an electrical vehicle, so you need a bigger size capacitor. So we are
Hmm.
working in our lab for the research purpose.
I see. Okay, and then the last question is, what is the specific capacitance achieved by the material?
That I have shown it in one of the slides. This is 198 farads per gram, which we have achieved. Let me this shows this electrochemical studies. So from this galvanic charge discharge this thing, we calculate the area under the graph, and then we have some formula. We calculate this value. So this is 198 farad per gram, which is the maximum which we have achieved so far.
Okay, thank you so much. Those are all the questions. Thank you so much for presenting.
Thank you so much. So should I stop sharing?
Yes, please.
Okay, thank you.
I will.
Thank you so much.
Thank you.